Now we're ready to learn about norms of vectors, which is a measure of the geometric length of a vector. For any n by 1 column vector, v1, v2, vn, let's define the norm of the vector as the sum of the squares of all the entries square root. The notation we'll use for norms are these double bars on both sides. It's easy to note that that's just the square root of v transpose times v, because v transpose times v gives the sum of the squares of all the entries. Let's take an example. V is the column vector 4, 3. We might interpret this in rectangular Cartesian coordinates as 4 units in the horizontal direction and 3 units in the vertical direction, giving that vector. The length of that vector is, by Pythagorean's theorem, exactly 5. And that's what this Euclidean norm generalizes, Pythagorean's theorem, with that type of interpretation for the components. In Matlab, you can just do an example, create a random 5 by 1 vector, compute the norm of v using the norm command, as well as compute the square root of v transpose v. In both cases, you'll get the same value. For this type of calculation, always use the norm command in Matlab. It's implemented a little more robustly than the square root of v transpose v, especially with regard to round-off errors, and either overflow to infinities or underflows to 0. The function norm won't have any problems if the norm of v is somewhere between the smallest representable positive number and real max. This square root of v transpose v can turn into infinity or 0 because of the squared nature of the inner calculation there, v transpose v, and then the square root can't undo that because the expression's already been rounded to 0 or infinity. So, in Matlab, subject to the finite precision limitations of the computer, use norm to compute this expression. Let's look at some properties. Take v and w as vectors and alpha is a scalar. First of all, we notice that the norm of v is always greater than or equal to 0. It's the square root of the sum of some squares. It's also equal to 0 if and only if v is the 0 vector, which we'll notate as 0 sub n. The only way we can get 0 out of that sum is if every entry of v is 0. Negative entries of v ultimately create positive contributions because they're squared. If we scale a vector by a scalar, well, the norm of that is just the absolute value of the scalar times the norm of the original vector. So scaling a vector by 2.5 changes its norm by a factor of 2.5. And there's something like Pythagorean's theorem, which says that the norm of v plus w squared is the norm of v squared plus w squared if and only if the inner product between v and w is 0. So this inner product being 0 is some notion of orthogonality in this generalized sense. The proof of this is quite simple. Take v plus w squared. What is that? Well, it's v plus w transpose times v plus w. Expand that out into 4 terms. Combine the w transpose v with the v transpose w as 2 terms, and we end up with this. Clearly, the original equality holds if and only if this inner product here is 0. Lastly, there's something called the triangle inequality, which says that the norm of the sum of 2 vectors is always less than or equal to the sum of the norms. It takes a few steps to prove that, and we'll do that on the next slide. The proof uses the Cauchy-Swartz inequality. Let's see how it goes. Take any vectors v and w that are both n by 1. The claim is that the norm of v plus w is less than the norm of v plus the norm of w. Let's derive this. Start by looking at the norm of v plus w squared. We know that's v plus w transpose times v plus w. That turns into v transpose v and w transpose w, which both become the norm of v squared and the norm of w squared, as well as 2 times v transpose w. We've done that expansion now a few times. Replacing the middle term by its absolute value creates an inequality. The Cauchy-Swartz inequality bounds the absolute value of v transpose w with the norm of v times the norm of w. And this is exactly a perfect square. Norm of v plus norm of w squared. Now just take square roots of both sides, and we end up with the triangle inequality as desired. Let's look at a picture of the triangle inequality. Take a vector v and a vector w, and the vector sum is v plus w. Now let's look at these lengths. That's the length of v plus w. That's the length of v, and that's the length of w. Therefore, it's very clear that the length of v plus w is less than the length of v plus the length of w. And that is the conclusion of the triangle inequality.